All right, welcome everybody to this seminar. So today we have Wang. Here's associate professor in the visualization and computer graphics groups at the School of Computing in University of Leeds. He's also a turning fellow and academic advisor at the Commonwealth Scholarship Council and the director of high performance graphics and games engineering, as well as an academic lead of the Center of Immersive Technology at Leeds. His current research interest is mainly in computer graphics, vision, machine learning, and applications of all of them. And previously, he was a senior research associate at Disney Research at Los Angeles in the US. And he received his PhD and did a postdoc in the School of Informatics, University of Edinburgh. In fact, that's also where I started to meet her like 15 years ago, or maybe a bit more. So when we were studying our PhD together in Edinburgh, so that was good memory. So I'm very happy that her is actually coming here today and have a chat with us. Okay. So without further ado, I'll pass the floor to you. So you can feel free to share the slide and do whatever you want. Yeah.
Okay, fantastic. Thanks, Hubert, for the invitation, and thanks for coming to the seminar. Hopefully this is going to be a casual thing, so please just interrupt me whenever you have questions regarding my presentation. I'm going to share my screen. Hopefully this would work. Thanks again for the introduction. And my background is applied machine learning in computer graphics and computer vision. Over the years, we have been doing a lot of part of the research is the character animation. So that's how I got into analyzing human motions. Recently, this line of research started to branch into some sort of the newly found niche we established. And that's why I chose to talk about this whole project in the past 2 years and share some experience with you. So the project is called the Universal Vulnerability of Human Action Recognition Classifiers and Potential Solutions. So why we're interested in this kind of direction, right? So nowadays, deep learning based classifiers are extremely popular, right? They're used everywhere. For example, in computer vision, they have been used for recognizing objects, recognizing activities, etc. And almost since day one, when deep learning became like popular, it is known actually the trained deep neural nets are extremely vulnerable to strategically computed perturbations, okay, on the input data, by the way, so which is called adversarial attack. So essentially, it means that for your trained classifier, if it can smartly compute some perturbation in your data, then that would completely mess up your classification. So why it's dangerous is actually that attacks are essentially imperceptible to humans, but they're very destructive to machine intelligence. Okay. Since then, adversarial attack as an independent research field has emerged. And people have tried this on different data sets, for example, images, videos, finance data, 3D meshes. And since it's a wide universal vulnerability has been identified in deep learning classifiers, then in a lot of areas, it has caused serious concerns. For example, like in safety, security, for example, like a life or time critical task like self-driving cars. Okay, so within this general broad background, we, in this project, focus on the skeleton-based activity recognition. Why? Because we are interested in human motion, and the skeleton data has been used as a kind of a key data type in many applications. For example, recognizing what people are doing on the street. And more importantly, as I mentioned, it's a newly found niche. So the whole research on adversarial attack and defense hasn't been very well explored in this domain. So that's why we come in, right? Proposing new attack and defense methods. So for those who are not so familiar with what adversarial attack is, I can give you a very simple example. So it originally started from a piece of seminal work, actually, presented by Sagdi et al. In 2013. So imagine you have like, I just need a pointer here, it's going to be easier. So assuming that you have a binary classification problem. You have two types of data that represented as blue dots and yellow dots. Now you train a classifier, which is a G theta, where G is a network, for example, then theta is your network weights. So those are parameters of the classifier. Then after training a very good classifier, the classifier should be able to draw a boundary, in this case, shown by as this brown line, between the two types of data so that it can classify the samples very well. Then in the very beginning, the research presented in this piece of work was saying, okay, we could actually compute a perturbation, which is represented by R for a specific data sample X here. So that is when we add that perturbation R to X, we end up with a new sample, which is the XR, okay? And X plus R will look very similar visually to X, but actually it will be classified as the other class. So it's essentially mess up your classification, okay? So the specifically what they did, actually, the way they did it is to through optimizing a very simple, actually, optimization problem, okay? At least here, the specific mathematics are not very important, but essentially they try to compute the minimal kind of a perturbation R that is available for a specific data sample X, so that after adding that perturbation to X, you'll get some new data sample. This is what we call the red dot here is what we call adversarial sample or adversary of X, okay? So it will give you a very different classification result. So in the work, what they showed is for a specific classification task, for example, given an image, which is X, then they can compute a perturbation like R for this image. This is like a noise type kind of pattern, right? Then we add this R to this X, you end up with this X plus R, okay? So visually, these two images you can see, they look very, very similar. If you don't pay attention, you don't really notice difference. But actually, the classification results on a trained classifier are totally different. So that's why we said this is imperceptible to humans, but very destructive to machine intelligence. Nowadays, if you Google, for example, adversarial attack, you'll see a lot of results coming up very, very quickly. They even already have a wiki entry, so which shows, from a certain perspective, how popular this research field is getting. So specifically for our research, we focus on human activity recognition. Okay, so in terms of human activity recognition or HAR, normally involves a very important type of time series data. Right? We can recognize what people are doing via videos, images, skeleton, motions, blah, blah, blah. So in this case, we focus on the 3D skeleton motion data because they are heavily used in various HAR solutions because they are robust to, for example, lighting, occlusions, and other ambiguity that would generate from videos and images. So a typical example of here skeleton motion would look like something like this on the right. It's a wear a shoe kind of motion. So it's a skeleton motion. Okay. So when we look at this type of motion under the context of adversarial attack and defense, we notice that actually they are very different from traditional data types, right? The first of all is it has a lower dimensionality. So in every frame, if you think about it, the skeleton would have less than 100 degrees of freedom. It's because normally, for example, if you represent the whole body with the 25 joints, and you use the joint positions to represent the pose, then actually that would give you, well, 25 times 3, 75 degrees of freedom. So it's far less than 100 degree freedom. So this is very low in terms of, well, when you compare it with the image, which has like millions of pixels, right? In this case, one consequence is you have a smaller space to compute your attack, which makes it more difficult. The second one is actually has to do with the motion itself and the human perception. So if you were to perturb, for example, a skeleton motion as you do for images or videos, normally you end up with perturbing like single joints or single frames. And for motions, that would totally disrupt the dynamics of the motion, which would be very visually noticeable, which means that your attack is not going to be imperceptible. So those are two typical difficulties when you try to do adversarial attack to skeleton-based motions. So in the first piece of work down the line, we proposed a new adversarial attack method where we also show that there's a universal kind of vulnerability of a wide range of state-of-the-art skeleton-based action recognizers. We also designed a new model that would enable us to compute such adversarial attack samples or adversaries, sorry. And we also looked into the role of motion dynamics in terms of the imperceptibility of adversarial attack of this specific type of motion. So very briefly, okay, we call it SMART. It's a cheesy name, but it's very memorable. We call it SMART. Called a skeleton motion action recognition attack. Okay, so when we compute the adversaries, we essentially do optimization. So here, Q means the range of motion. Q hat means actually the adversarial sample we're trying to calculate. So we calculate Q hat by minimizing this objective function, which has two terms. So one is what we call a classification loss, one is the perception loss. Okay, I don't want to get into too much details of the mathematics here, but it's really, really simple on the high level. So the perception loss contains two terms. One is the bone length loss, one is the dynamics loss. Okay, so the bone length loss is essentially saying you can perturbate in whatever way you want, but you want to keep the bone length a constant, right? Because the bone length normally don't change. And we found in a perception study, actually, the bone length change would have easily caused suspicion. Okay, so that's one term. The other term is we want to match the dynamics of the adversary to the original data sample, which means that we start to do the minimize the L2 norm of the zero order information, first order, second order, third order, up to nth order actually. So in plain language, that means actually that the zero order would be joint positions. The first order would be joint velocities. The second order would be joint acceleration. Then you have snap, you have a jerk, you have other things for higher order information. So these are the two terms of the perception loss. For classification loss, it's even simpler. It enables us actually to initiate a different kind of attacks, like different modes of attacks. For example, say if a file represents a trained network, then we can do like what called anything but A/B attack by minimizing this this negative cross entropy. Essentially, this is maximizing the cross entropy. This is essentially saying on high level, essentially saying, okay, I want the class label of the adversary to be different from the ground truth. As long as it's different, that's okay. So this is the easiest attack mode. Then we also have anything but ABN attack, which is essentially saying, okay, where we maximize the entropy of the prediction. So make your prediction flat as possible over all class labels. So that we say, okay, as long as the predicted class label of the adversary is not in the top n class in the prediction, then we think we're successful. So this is aiming for classifiers, who not only measure like a top 1 accuracy, but also top 5, top 10, top n accuracy, right? The third is a specific attack. So essentially saying we'll minimize the cross entropy between the prediction on the adversary and a specific class label. For example, I want to attack a walking motion to be a run motion, specifically run, not just any not walking motion, right? So this is the most difficult one. So very quickly, I can show you what it looks like. Okay, there are 3 groups of motion here. So in each group, the left is the ground truth, and the ground truth label is above the motion. And on the right, in each group is the attack motion. Okay, and after you can see the after attack label. So visually, you can see that you can spot any difference between these two motions in each group. Then that means our method fails, right? If you can't easily spot any difference, that means we have succeeded. Okay, so we have done, by the way, we have done very rigorous perception study on this one. Normally, people can't really tell the difference before and after attack, but you can see that the classification results are totally messed up. So visually, that's proof that the success of this algorithm. Very simple one. So more, I can give you some numerical results here. We tested the method onto, well, in this case, 5 state-of-the-art action recognizer. We tested more than 5, but here I just show 5 on 3 data sets, okay, across 3 different kinds of attack modes. You can see that, of course, the specific attack mode is the most difficult one because it's actually, this is the attack success rate is the lowest overall because, well, attacking, for example, attacking a slow walking motion to a faster walking motion is easier. But if you say, I'm going to attack a walking motion to a sit down motion, that's, of course, much harder. But in the easiest attack mode, you can see that the success rate is really, really high. On a lot of almost all classifiers across all data sets, the attack success rate is almost 100%, which means that it's totally ruined your trained classifier in this case. Okay, so before, in addition to the numerical results, we also say, okay, this is Whitebox Attack. We could use Smart for a transfer-based Blackbox Attack, which means that we can use Smart to attack a service classifier, right, in a Whitebox Attack mode, then use the computed adversaries to attack other models. So this is like what we call a transfer-based Blackbox Attack. We also did, like we mentioned, a very strict perception study to see if people can visually spot any difference before and after attack. And it turns out it's been quite successful. So that's the very first piece of our work, which is a Whitebox Attack on skeleton-based action recognition. So it has a high success rate. It can do transfer-based Blackbox Attack. It's very highly unperceivable to humans, and it actually proves that basically existing activity classifiers are all vulnerable. So this is very quickly the first piece of work. Then we move to actually the next. Well, by the way, again, if you have questions, just interrupt me. Okay, I'm going to move on to the next piece of work here. So based on SMART, we know that SMART is a white box approach, which means that when you try to calculate the adversary, you need to know the full details of the trained classifier. For example, how many layers, what types of the types of layers, the weights, the trained network weights. You have to know all of that. So which makes it a little bit unrealistic, right? So then we naturally ask the question, what if we don't know the details? Okay, we are only allowed to make queries to the network and get for example, I put a motion in, all can read is the output, the prediction of the network. Okay, what should we do? Can we still attack this one? Yes, this is actually a typical black box attack setting. Turns out we can do that. So here we propose a new method called a bazaar. It's a black box attack on skeletal action recognition. So in this work, actually, other than the vulnerability of existing classifiers, we found something else. So first of all, in the black box attack, we still have to address the problem of low dimensionality of a possible solution space, as well as the perceptual sensitivity of him. Right. In addition to that, we found that our algorithms can find a lot of adversarial samples on the motion manifold. So they are essentially unmanifold adversarial samples, which is very different from the findings of existing research. Because before this paper, people tend to believe that all the adversarial samples are off data manifold, not on data manifold. But I can show you later, there's a wide existence of unmanifold adversarial samples in skeletal-based motions. So the specific method here is very simple. I'm going to give you a high-level review. So imagine you have a classifier boundary, which is indicated by the light blue line here. Okay, that's a DCX. Okay, then imagine you have a motion manifold, which is represented by M, the black line here. Okay, so given motion X, we want to compute its adversarial sample, which is X prime. But we propose to compute X prime by optimizing this function, okay? So we're minimizing the difference between X and prime with respect to certain loss function. Subject to that, actually, the adversarial sample is contained within the box, essentially a high dimensional box, while saying that X prime has to be on the motion manifold. I'll give you more details later. And then the predicted class label of X prime is either a specific pre-given kind of a class, which is C. This is essentially a targeted attack. So you have a goal class label, you want to attack the current data samples too, right? Or it's just on target attack. As long as the predicted class label for X prime is different from X, then we're happy, right? Then clearly, this is a very nonlinear optimization problem, right? So we propose the iterative approach to actually solve this optimization. So it has 3 steps. We iteratively carry out 3 steps, right? The first one is called random exploration. So given X here, we sample a class which is also on the manifold, but on the other side of the boundary. Okay, it's a different class, right? We start from there, then we do random exploration. So the math here a little bit messy, but essentially what we do is actually we want to sample kind of things close to X1 prime, but still on the right hand side of this classification class boundary. Okay, then we pick one. Okay, say we pick this one. Then we do the second step called aim probing. Essentially, we move X2 prime towards X. Okay, so it gets close, very close to the boundary, and we stop there. That will give you X3 prime. Okay, then we do X3 prime. We do manifold projection. We project this S3 prime to the manifold, which will give you X4 prime. Okay, so the manifold is also projection is also done by minimizing this loss function, which is essentially saying, okay, I want to minimize the difference between the current adversarial sample and the predicted adversarial sample. And also I want to minimize the difference of the second order derivative of both motions. Subject to, okay, this is high level, so the bone lengths don't change. B stands for bone length in both samples, okay? So the bone lengths don't change. The joint angles don't violate joint limits, as well as, of course, if we have the targeted label or targeted attack label. So subject to all this. So let's not talk about the details because this part should be part of the background anyway, right? So more details can be found in the paper. After we do the projection, then we get X4 prime. Then we do random exploration and the probing projection again, iteratively after many iterations, then finally we'll be able to find a good classification, a good adversary X prime that is both near the boundary, but on the other side of the boundary, classification boundary, and also on the data manifold. So when the X prime is on the data manifold, actually it looks very natural. So the attack will still be very hard to spot. Okay, very quickly, we evaluated, okay, first of all, we found that a bazaar can always achieve 100% success rate. Okay, then we start to think we need to evaluate the quality of the attacks. So we use the 4 metrics. Okay, so one is the after perturbation, the joint position deviation. The second is the joint acceleration deviation. The third one is the joint angular acceleration deviation. And the fourth is the percentage of the bone length deviation or violation. Okay, normally, if we compute that to the adversarial samples, right, the lower the better. So these are the results for on target attack and target attack. Okay, we tried that on 3 data sets. That's HDM05 at the top, and TU60 in the middle, and the kinetics at the bottom on 3 classifiers. Okay, STGC, MSG, 3D, and SGN, 3 state-of-the-art classifiers. Also, we did a little bit kind of ablation study on with and without manifold projection. So this is to test how many actually, for example, adversarial samples can be found on the manifold. Okay, so this is a brief kind of results. Normally, overall, of course, the adversarial samples calculated by Bazaar are very good in terms of metrics, but I would like to draw your attention to this particular metric, which is the on manifold. The larger, the better. Okay, so you can see that this means on this specific classifier, a GCA, which is a very famous one, on this specific data set, HDM 0.5, then 99.55% of the adversarial samples are unmanifold adversarial samples, which means that visually they look very similar to natural motions, and it's very hard to spot the difference, before and after attack. So this shows that two things. Okay, first, the general belief that the adversarial sample are only exists off manifold is wrong. At least not true for all data samples. We have proven that it's wrong, at least for skeleton-based human motion. The second one is the danger of this kind of attack, because as was said, the attack motion look very similar and very hard to spot the difference between the adversarial sample and the clean sample. So that's the second piece of work. A brief summary. We proposed the first Blackbox attack on skeleton-based action recognition. It also achieves a high success rate and highly unperceivable attacks. Also, for the first time, we show the wide existence of unmanifold adversarial samples. Okay, so that's our second piece of work here. And of course, so far we have talked about existing classifiers are vulnerable, right? We have proven that by proposing new attack methods. Naturally, there's some ongoing work here where we investigate whether it's possible to defend them against attacks, right? Okay, so why we're doing this? Because the vulnerability of such classifiers are newly found by us. So naturally, we want to be able to defend these methods. And when we look even further, similar defense methods have been designed for other data types, like images, but they're not very effective on motions, again, simply because they're mostly designed for static data, which doesn't contain the dynamics in time series data at all. What's more important is for these defense methods, they all end up giving a trade-off between accuracy and robustness, which means that, for example, if you use the defense method to retrain your model, yes, the robustness against the adversarial attack would increase, but your natural accuracy would decrease, which means that your classifier is not as accurate as before, right? So this is believed to be an intrinsic trade-off between, for defense methods, which has been proved wrong again in our research. Okay, I'll show you later. So existing method, typical existing method, including two mainstream methods, which is one called adversarial training, then the second one is called randomized smoothing, or ATNRS. Okay, in this ongoing work, we propose our the first Bayesian energy-based adversarial training methods, what we call BEAT. Okay, a cheesy name, but very memorable, hopefully. So why existing methods don't work? Okay, I'll give you an example here. So this is an example we saw before. Given a binary classifier, you have a data which is a network weights, right? Given a network, you can train the classifier to draw a classification boundary between the two classes. Okay, where actually attacker can calculate a perturbation, right, to attack one data sample here. What adversarial training does is essentially to minimize this function. It solves the min-max optimization problem. What it does do actually is to, in the inner loop, it maximizes the loss. Okay, given the network weights, it maximizes the loss between a perturbed data sample and the given class label. For example, if sigma is some perturbation from some perturbation set x, then you add that perturbation to x. Okay, then you maximize the loss between given the current classifier theta and the perturbed class data sample, then the ground truth label. You want to maximize this. Okay, this is understandable because during training your classifier in a standard training setting, normally you want to minimize this loss. What they do is they maximize this loss in the inner loop, and they minimize the overall loss, minimize the expected maximum loss here. So essentially, it means that I want to find the classifier that could minimize the expected maximum loss for the perturbed data sample, leaving the mouth full, right? So graphically, you can understand that, okay, I want to modify the boundary a little bit to include that perturbed data sample to this side of this classifier so that I can still classify this data sample correctly, okay, even after attack. This is essentially what adversarial training does, okay? Comparatively, what RS, or randomized smoothing, does is, okay, I'm going to assume at each data sample, I can draw a random kind of a noise to pollute it during training so that I can redraw the classification boundary so that the classification boundary will include the whole area of around this data sample. So after training, even when I attack this X data sample, my trained classifier, my adversarial trained classifier based on randomized smoothing can still defend any perturbation within this range. So this is essentially what AT and RS do. Why they're not good? Okay, so first of all, if you think about it, in SMART and Bazaar, we have established that there's more than one adversarial sample corresponding to each clean data sample. For example, in this case, this is again a trait classifier, right? If we attack one clean data sample here, SMART would give you some, adversary that is really close to the range of data sample. But Bazaar, since it's based on sampling, it can compute a lot of actually, adversarial samples. So essentially, that means there's a one-to-many mapping between the clean data sample and the adversarial samples. Okay, then both these methods, they don't really consider the distribution of the adversarial samples, which, by the way, can have arbitrary shape, right? They don't really consider the whole adversarial distribution. So I think that's why they're not really, well, that good. The second reason is actually when they minimize this optimization, essentially what they're looking for is one classifier. So essentially, this optimization is what we call a point estimation on the classifier. Okay, what does it mean? Okay, imagine you have two data sets here, blue dots and the yellow dots. There are actually more than one classifier that would give you a perfect classification. For example, you could have theta representing this curve. You have another theta representing this curve. You have another theta representing this curve. So they all represent different network weights, essentially different models. Different model would draw different boundary classifications. Okay, so why that's important? Okay, I give you an example here. Still, the same four adversarial samples we can compute from SMART or Bazaar. You can see that, for example, for this middle classifier, it's naturally robust to these three perturbations, right? It's not robust against this one, but actually it's naturally robust against these three. Okay, so this guy, it's not robust against any of these. So that means actually we know there's a distribution of classifiers which would all give you perfect classification, but their robustness against the adversarial sample are very different. So we need to consider them when defending adversarial attacks, right? So the key idea here is, okay, we instead of just model the class and the data and the class labels, we propose to jointly model the data, the whole adversarial distribution, and the classifier together. So we essentially want to model P, theta, X tilde, and Y. So theta is the network weights or your classifier, X is the clean data, X tilde is the adversaries, and Y is the ground truth label. So we'll propose to jointly model all the four basically factors here. Okay, how do we do this? Okay, we start from a very simple one. We start from any discriminative classifier, right? So based on a very new paper published by Graswell et al. In 2020, so any discriminative classifier is actually can be interpreted as an energy-based model. Okay, for example, say in their paper they say, okay, if you model clean data X as a probabilistic distribution, P theta X, where the theta is actually your model parameter. So you can actually parameterize this by an energy function, which is exponential 2 minus energy function, that's a capital E theta X. And then this actually can be further expanded into, for example, if you have a classifier here, okay, then which is represented by G. This network G is parameterized by network with theta. Okay, this is essentially saying if you pass a class, if you pass a data sample X through your network, then the network will have a prediction or predict distribution over all possible class labels, right? Then you want that to spike on the class label that is the same as the ground truth, which is Y. So you want this number to be as big as possible, essentially. Okay, so Px actually can be represented as an energy model in this case. You see here is this is exponential function, so this is energy. What we know is that we don't know the specific shape of Px, but what we know is in the data space, we will have observations X. This will be high. So the energy will be low actually, so that this whole number will be high. In this case, because this number is not normalized, the energy can be, well, it's not bounded. So it's not, technically speaking, it's not a probability distribution. Probability distribution, the integral of a probability should be 1, right? So they comes with this Z theta, which is an intractable normalizing constant. So in this case, actually, any data set can be represented as an energy model. Okay, then given this interpretation, any discriminated classifier can be seen as optimizing this joint probability. P, X, Y is the ground truth label, X is the data. So if you look at this one, you're summarizing over all the, you're also considering Y. So P, X, Y essentially is this. Okay, it has a relatively simpler form than this one, but this is still straightforward. So training this one is just to maximize the log likelihood of this joint probability, which will give you these two terms. You can easily see this actually becomes a normal classifier. This is exactly what we want to do, right? Given X, we want to predict this classification label. This is what we essentially do when we normally train classifier by, say, minimizing cross entropy. Okay. What the difference is, this energy model actually has an additional term, which is this one. You also want to maximize the Px. It turns out this part is a normal classifier, then this part can lead to a better accuracy, better robustness, better out of distribution detection, blah, 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 blah. So essentially the takeaway message here is by reinterpreting any discriminative classifier with an energy-based model, you have a better classifier. Okay, so starting from this example, okay, we're gonna say, okay, let's also think about adversaries. So this is novelty 1. Unlike this method, we first do a Bayesian treatment on all the adversaries. So essentially, we're modeling the whole distribution of adversarial samples. Okay, so we decided the energy model would look like this. So the same thing as before, but we add this term. Okay, so we want this value to be high because even after perturbation, we want the classification to be the same. Okay, so we want this part to be high. We want this part to be low. Okay, lambda is the weight, and D is a distance function, which measures the similarity between the original sample and its corresponding adversarial sample. Of course, the more dissimilar they are, the larger this part is, the lower this overall value is going to be. Okay, so we essentially incorporate the X tilde so that we can consider the whole distribution of the adversarial samples. Okay, this part can be, of course, naturally decomposed into 2 parts. Okay, so this one is the same thing here. This is a normal energy-based classifier. Okay, we already know how to optimize that. This part you can see, interesting. When we calculate this part, this is the joint probability divided by this joint probability, where the Z is the intractable Z will be very conveniently cancelled. So what you have is here. Okay, so in this case, this essentially becomes a conditional distribution of all the adversarial samples based on clean samples, which is, well, sort of making sense because do you remember, for every data sample, clean data sample, we can have a distribution of adversarial samples, which is a one-to-many mapping. So naturally, this distribution will be conditional distribution. Okay, so this is step one. Okay, now we specify what a D should be. Okay, this similar function actually can be anything, to be honest, if the data, if it's an image or if it's a finance data. But in our case, I think it should be specific, domain specific. So we use a similar example as before in Bazaar to compute the distance. This is again bone length. This is the mismatch between the several orders of the derivatives of the motion. So K represents the kth order derivative. So essentially, this means that we still consider the zero order, first order, second order, blah, 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 blah. This is the bone length deviation. So we use this as a distance function, okay, to sample essentially all the adversarial samples around a given X. Okay, so after specifying dx, we have a full representation here. Okay, step one. Step two. Now we already know how to incorporate X delta into the probability. Now we need to think how we can incorporate the classifiers. So we expand this further to incorporate theta. Okay, theta is the classifier weights. So this is novelty two. We also do a Bayesian treatment on classifier. Essentially, we're modeling an infinite number of classifiers in this case. Okay, so this joint probability can naturally be decomposed into these two. Okay, then this one essentially is just this one, right? Given theta, then this is the same as a previous p x delta y. Then we have one more, which is the prior of the classifier. Okay, so imagine we can train this. Then during prediction, we can use Bayesian model averaging. Okay, say we train this and given a new data sample x prime, we want to predict the class labels of x prime, which is y prime. Then this can be computed by the expected, the average, or expected prediction across all possible models. So we draw a lot of theta from p theta. Then each theta represents a different classifier, and each classifier would give you a different prediction. Then we average basically over all prediction. So that gives you the final prediction, right? Say we average over n possible thetas with essentially n possible classifiers. Then that will give you a more reliable prediction here. Okay, so this is, if we can train this, we can do a prediction this way. However, how we solve this, okay? It's actually, first, why we're doing this has a theoretical background, okay? So optimizing this one is quite similar to optimizing this one. If we use a flat distribution, like a uniform distribution for p theta, then iteratively apply maximum posterior right estimation onto this, okay, onto this distribution. That is actually very similar to doing stochastic gradient descent on this one. But again, theory has shown even with a flat prior, your posterior distribution can be very, very, irregular, which essentially means that some classifiers are really good at classifying things and some are not. Then to be able to explore the full space of the posterior, we still need to do this full Bayesian treatment on the classifier. This is a little bit of theoretical background. Okay, however, numerically, it's not very easy to do. Why? Because first of all, the posterior space is very big. Okay, the posterior space here is very big. Imagine how do you know what kind of prior you want to put on your network weights when you train network, right? It's very big, it's millions of parameters. How do you do that? The sampling is very, very slow. The second one is if we were to do this, we essentially require retraining the classifier from scratch, which is a very inconvenient and sometimes impossible because a lot of classifiers are very big. They are pre-trained. So a lot of users just use the pre-trained model, fine-tune their own data set, right? It's not very desirable to retrain the model from scratch. If you apply the adversarial training or randomized smoothing as existing methods do, they do require retraining from scratch. The third one is retraining has another disadvantage because it could undermine the learned features if your classifier is trained under, for example, multitask learning. When you train the features, it's also going to be used for other tasks, not only for your classification. If you train the whole classifier, you're gonna undermine those learned features, right? So for all these reasons, we propose a third novel thing we could do, which is a post-train strategy. What we do is very simple. We append a very small network. In this case, it's just a 2-layer MLP, F network, 2G. Okay, assuming G is the given classifier you trained already, where the network weight is theta, we just append that in 2G, append the small network. It's 2-layer MLP, which is parameterized by theta prime. Theta prime is the network weight of the 2-layer MLP, right? Then we do some sort of in a residual network kind of way. So basically, we take the output of the G theta as the input of the prime, F theta prime. Then we sum the two outputs. Then that would give you the final logics here. So this way, we don't retrain G here. Okay, you have trained that already, which is very big. We only train F. Okay, since F is very much smaller than G, the retraining is really fast. And additionally, in this case, G can be treated as a black box. We don't have to know any details about G. We just have to know the input and output of G. Okay, so we focus on training the theta prime F. How do we do this? Okay, adding this essentially turns this prediction problem into this one. The only difference between these two is the introduction of theta prime. Okay, we assume right now theta is a given and do not change. We do not touch theta at all. We just train theta prime. Okay, so that's essentially just adding one more parameter into this optimization problem. Okay, so when we do inference for this one, we have to do inference by alternatively sampling the network weights and doing optimization on, well, essentially maximizing the likelihood of the probability distribution. In this case, for example, we first do maximum likelihood optimization for theta prime of x delta tilde and y. Then we fix that. Then we sample theta prime. Okay, we do this alternatively. Remember, this is just the previous simpler distribution. Okay, where we only consider the clean data, the clean label, and the adversarial samples. We do this 2 steps alternatively. Specifically, when we do maximum likelihood, we just decompose this to 3 terms, where this one is again a normal classifier, right? Given clean data, we want to predict the class label. So this part can be replaced by minimizing cross entropy. These two cannot be directly optimized because they have intractable terms. So we use stochastic gradient Langevin dynamics to sample them. Okay, we will leave all the details to if you have questions about details, we can talk later, and they're all available in the paper anyway. So that's the maximum likelihood sampling. Then for sampling the network weights, we use essentially Monte Carlo sampling. Specifically, we use the stochastic gradient adaptive Hamiltonian Monte Carlo. Sorry, that's a very mouthful name. But anyway, this is just a numerical details, right? We do these 2 maximization, sampling, after n iterations. We pretty much train the network. Okay, so some results. Sorry about the big table here. We tested the classifiers. We tested these 4 state-of-the-art classifiers on 3 data sets, HDN 0.5, NTO60, and NTO 120, under 6 different training schemes. ST means standard training. Smart AT means adversarial training based on smart. RS stands for randomized smoothing. Then we also have other 2 defense methods called the MART and the traits. They are the state of the art for defending image data, not motion data, right? We're just using my baseline. So you can see that in each experiment, we have 3 columns. The first column is accuracy. Okay, after training, we test the accuracy. You can see that sometimes after our training, the accuracy even slightly higher than the standard training, which means that in general, there's no trade-off between the robustness and the accuracy. Okay, that's the first thing we have proven, which is widely different from the general belief, which is there is an intrinsic trade-off between accuracy and robustness. Okay. The second one is we use the two whitebox attack methods on split motion data, which is called SMART, which is our own, and CSA with somebody else, from somebody else, right? Consider that after training, their attack success rate is much lower than any other training methods here. This works essentially across all different data settings. This is we did more than 120 something experiments across different data sets, across different classifiers, across different attackers, combined to see that beat our method achieves universally better results. What's even more surprising is we use SMART to attack models trained under different training schemes, defense methods, basically, right? Since SMART is an iterative method, the more iterations you have, the stronger the attack is going to be. So we really run SMART for a long time, and then like 1,000 iterations. You can see that on the vertical axis, that's the attack success rate. Okay, on the horizontal axis, that's the attack iterations. So when we use more and more iterations, all other defense methods, including the standard training and all the other defense methods, they eventually will fail. Okay, on these data sets, you can see the attack success rate will become 100% from some certain point, which means that all the defense methods will fail at a certain point. While the red line is the beat, you can see that we can always resist attacks to a certain extent, not equally good. Now this is on Whitebox Attack. On Blackbox Attack, we use the bazaar to attack our beat trained models and evaluate the results. Essentially, we also use the 4 metrics. If you remember, I talked about before how we evaluate the bazaar. And essentially, overall, the method is we make the adversarial, we make the quality of the adversaries really worse than before, which means that actually if you still attack the model after beat training, then your attack will be much more perceivable by humans. Essentially what on high level what this is. I'm just aware of time, very short summary. We proposed the first defense method on solution-based action recognition. It has a really good, a high robustness increase, and it's trained things very fast. It has a black box nature, and it's very effective against the various attackers, across data sets and across different classifiers. Oh, by the way, this piece of work, the defense method, it's still under submission, so I'd prefer if you don't share it with others. But well, not exactly, but technically speaking, we have uploaded this into archive, but not with the full details. So summary of summaries in this project. Okay, we know that human activity recognition is a very important task, but the robustness, especially under adversarial attack and defense, has not been fully explored. So in this project, we have proven that existing classifiers are very vulnerable to adversarial attack. But the good news is they are all defendable, because we also proposed our very first defense method on that. So in terms of framework, future work, we would like to explore more theoretically the reason of vulnerability of motion-based classifiers, and how this, while this is relatively well researched for static data, it's not. I don't think it's a very well explored on time series in general. And we would also like to explore other kind of representations of other types of data, time series data, like a financial data, like a videos, other types of time series data. So in this talk, I mainly used 3 of our recent publications, 2 from CVPR last year, and 1 is under review. So thanks to all my collaborators from 4 different universities in 1 company, and great thanks for their great effort on this one. And thank you for listening. Any questions welcomed. I'm not sure, I'm pretty sure I've
any questions?
Run off on time already, I think.
No, it's all right. We can always have a few questions.
Hello, Dr. Wang, can you hear me?
Yes, I'm sorry, just to stop sharing so that I can see your face. Yeah.
Yeah, I have questions about that. In SMART, you use acceleration loss, but in BASA, in the black box method, you do not use it, you use angle loss. But so which one is the better restriction, the acceleration loss or the angle loss?
Acceleration or the angle loss? Do you mean joint angles?
Yeah, joint angles.
We never did joint angle.
In the bar
Smart. In Bazaar we did, yes. In Bazaar we did. So Smart was done in the context that we don't really respect the data manifold. So we assume that you can violate joint limits, actually, as long as it's not visually noticeable. And what's wrong with that is it's not implementable, right? Because if you're a real human, you cannot violate joint limits. So that's partially why we start to think about a Bazaar, where we have to think about the data manifold. Because if your adversarial sample is on data manifold, it's actually totally implementable by real humans. That's where we start to consider all the joint limits on the joint angles.
Okay, I understand. Thank you.
Yeah.
Any other questions?
So maybe this is not something you guys do on a daily basis.
That's something that I'm quite interested in. But actually, I'm quite interested in your defending the adversarial attack research that you include in the last. I'm just wondering whether this can also be considered as a domain shift problem, or if there's any similarity with the domain shift problem. So essentially, it's like your adversarial sample is like a new type or new distribution of data that is slightly different from the original distribution, right? So you wish to shift the classifier such that it will be able to adapt to the new types of adversarial samples. So this somehow is similar to the problem definition of domain adaptation, right?
Yeah, definitely. I mean, right now we think it's likely to be domain specific, because if you think the data sample is like a sheet, right, in a high dimensional space, then the adversarial sample distribution is likely to be like a thicker sheet around the data sheet. So the reason we believe that is the case, at least for splitting data, is because the way we define the similarity function between clean sample and adversarial sample, which is based essentially on the bone length and the dynamics. So if you say you want to use beat on other data sample, for example, on images, on videos, on finance data, stock market data, for example, then that D has to be different. Otherwise, there's no good measure of similarities between clean sample and the adversarial sample. So in that sense, I think it's the beat framework is general, but the D has to be specific. The distance function or the similarity function has to be specific for domain.
Yeah, that's
for
right.
Specific domains. Yes.
That's right. Interesting. Right. I saw a few people leaving because they need to attend another meeting. So if I receive any questions from these people, I'll probably forward it to you, and we can also keep the conversation offline as well. Yeah.
Definitely.
Yeah. All right. Thank you very much for giving a talk to us. I think it's very interesting, and I hope we can work more on these kind of topics in the future.
Definitely. Thank you.
All right. Thank you very much, guys, for attending as well. See you next time.
Bye.
Thank you. Bye.